Topic 4, History of Earth, Lesson 1, Determining Ages of Rocks, pages 154 to 161. As always, we're going to start with the connected. So the first thing we need to do is draw an arrow pointing from the youngest rock to the oldest. And how many rock layers do you see? So in your workbook, you should draw an arrow pointing downward from the peak to the bottom. I would say that there's about 5 to 6 layers in that specific mountain or hill. So this is Rainbow of Rock Layers, Figure 1. Many colorful rock layers make up the hills of Arizona's Painted Desert. These rock layers represent many millions of years of Earth's history. How did you decide which rocks are the youngest and the oldest? So the oldest rocks are buried the deepest, so they must be on the bottom. That also means that the youngest rocks must be at the top. Suppose you were the first person to study the canyon. How could you find out exactly how old the oldest rock is? And the sample answer would be, I could take rock samples from the bottom of the canyon and conduct tests to find out how old the parts making up the rocks are. I could look for fossils of a known age in the rock. Describing the ages of rocks. So geologists have 2 ways to describe the age of a rock. Age relative to another rock and age in number of years since the rock formed. So relative age is a rock's age compared to the ages of other rocks. Example, if you say that you are older than your brother but younger than your sister, you are describing your relative age. Absolute age is the number of years that have passed since the rock formed. So if we were to go back to that example and saying how old you are, that would be how old you are since you were born. Reading check. What is the difference between relative age and absolute age? So relative age determines whether rocks are older or younger than other rocks, whereas absolute age represents the number of years that have passed since a given rock formed. Why do geologists want to analyze and describe the ages of rocks? It provides evidence of past events that occur in rocks. Rock layers form a record of Earth's history called the geologic record. And determining rock ages helps scientists organize past events to better understand Earth's history. Determining relative ages of rocks. So the position of rock layers. The law of superposition is the ages of sedimentary rock layers in undisturbed horizontal sedimentary rock layers. The oldest layer is at the bottom and the youngest layer is at the top. To understand the sedimentary rock layers, you use the law of superposition to find that the oldest layer is at the bottom and the youngest is at the top. So the higher you go up, the younger the rocks are. The lower or deeper you go, the older the rocks are. All right, clues from igneous rocks and faults. Igneous extrusion is when lava hardens on Earth's surface, and igneous intrusion is when magma hardens between layers of rock underground. So an extrusion or intrusion is younger than the rock it covers. That's because the rock was already there and then the lava happens. Or the magma occurs and it hardens there. So it's always going to be younger than what's around or underneath it. Fault is a break in Earth's crust, and a fault is always younger than the rock that it cuts through. All right, clues within rocks. Figure 2. Intrusions and faults can help to determine a sequence of events within rock layers. So the first thing we need to do is draw an X over the igneous intrusion and draw a line along a fault. So our igneous intrusion is here where everything's kind of coming together. We have the different colors of rocks there. Our faults are these lines here. Just note my lines are not quite on where the fault line is, so you can see the lines in your book on the image. But to be completely honest, drawing it with the mouse freehand is a little bit difficult because I was just using the touchpad and not an actual mouse. So next thing we're supposed to do, the rock layers are older or younger than any faults or intrusions that run through them. And we just said that the rock layers are older. 3. The San Andreas Fault runs for hundreds of miles through California. What occurs when rocks on either side of the fault move? And the answer to that is earthquakes. Using fossils. Fossils are the preserved remains or traces of living things, usually found in sedimentary rock. Index fossils, that is a fossil of an organism that was widely distributed and existed for a geologically short period of time. Scientists use index fossils to match rock layers and find their relative age. All right, so the model it on page 157. You can model how scientists use index fossils to match rock layers separated by distance. So we're going to use fossils to match rock layers here. At location 1, circle the fossils that you can use as index fossils. And we can use the spiral shell and I believe that one is a trilobite down in A. Both of those are good index fossils. Next, we're going to use the index fossils at location 1 to label the matching layers at locations 2 through 4. Then draw a line to connect each matching layer across all locations and shade them to the same color. So, all of these ones at the bottom have that trilobite in them, or what I believe is a trilobite. It looks like a trilobite to me, but it's kind of hard to tell in this particular image. Anyways, all of those are A, and you can tell because they have the same fossils within them. So you will label each of them as A, you'll draw a line through them, and you should color them all the same color. Then we're going to move up to B. So for B, there is just this one area that has the same fossils. Next, we're going to do C, and we know that because there's this spiral shell, it is in the top at location 2, in the middle at location 4. Finally, we have D, which is only located in location 4. Lastly, we need to answer, at location 4, what can you infer about the ages of rocks in history? Cite evidence to support your inference. And a plausible answer would be, layer B eroded away at location 4. The fossils indicate that the other layers match layers A, C, and D. Changes in rocks. So changes in rock layers makes it hard for scientists to reconstruct Earth's history. Unconformity is a gap in the geologic record. It shows where rocks have been lost due to erosion. Folding is forces inside Earth fold rock layers so much that they are turned over completely. So figure 4, we have unconformity and folding. We're supposed to shade the oldest and youngest layers in the last 2 diagrams, label the unconformity, and circle the part of the fold that is overturned. So here at the top and the bottom is what we need to color, and the unconformity is the top. Then on the bottom section, again, the top and bottom are colored in, and you should have circled the little kind of, honestly, it reminds me of a fidget spinner shape with an extended edge. So around there is where we need to have our circle, because that's where the folding is really shown. Reading check. In your own words, explain one of the methods that geologists use to find the relative ages of rocks. And geologists use the law of superposition, which states that in undisturbed horizontal sedimentary rock layers, the oldest layer is at the bottom. So when something is undisturbed, the oldest layer is always at the bottom. Now we just went over unconformity and folding, which are examples against this. So like, it's not against this per se, but they're examples of when this isn't happening. So the key part being that the horizontal sedimentary rock layers are not disturbed, In unconformity and folding, they are disturbed. So we're going to see differences there. So I just want to distinguish that. Next, determining absolute ages. To find absolute age of rocks, scientists use certain elements in rocks that change over time. Radioactive decay is when the atoms of one element break down to form atoms of another element. It's measured by half-life, which is the time it takes for half of the radioactive atoms to decay. So for this one, you can see kind of the graph here. We have it, the original sample is at 1. There is a time period when it cuts into half of its life. It goes to 1/2, what that time is, and then to 1/4, and then to 1/8, and 1/16, 1/32, so on and so forth. Radioactive decay and half-life. This is a sample element that illustrates radioactive decay. So in radioactive decay, we have an unstable atom. It turns into a new atom because energy and particles are released. So what pattern do you see in the graph? Use the pattern to complete the last bar. So we know that we had 100, then it's 50-50, then 25, then 12.5. So each time it's splitting in half. So this time we would do 12.5 divided by 2, and we'd have 6.25. Then the other part would be the remaining 93.75%. 2. The graph shows that as the amount of the old radioactive element increases or decreases, the amount of the new stable element increases or decreases. So our answers would be that the old radioactive element decreases, the amount of the new stable element increases. Radioactive dating. So radioactive dating is when scientists determine the amount of radioactive element in a rock element. Compare it with a stable element that it becomes, and use this information at half-life to find the age of the rock. So example, potassium-argon dating. Potassium-40 decays to stable argon-40 with a half-life of 1.3 billion years, which is useful to date very old rocks. Carbon-14 dating. All living organisms contain carbon. Carbon-14 decays to stable nitrogen-14 with a half-life of 5,730 years. This is useful to date living organisms less than 50,000 years old. All right, so now we're going to do the math toolbox from page 160. Use radioactive dating to calculate absolute age. So a rock contains 25% of the potassium-40 it started with. Use radioactive dating to calculate the absolute age. Determine how many half-lives have passed. After one half-life, 50% of potassium would remain. After two half-lives, 25% of the potassium would remain. Find the half-life of potassium-40. The half-life of potassium-40 is 1.3 billion years. Then we need to multiply the half-life by the number of half-lives that have passed to calculate the rock's age. So that we would take 1.3 billion years, multiply it by the 2 half-lives that have passed, and that'll be equal to 2.6 billion years old, which would be the absolute age of the rock sample we have. So now, doing our own, we have a bone that contains 12.5% of the carbon-14 it began with. How old is the bone? So we start with 100%. At one half-life, it is 50%. At two half-lives, it goes down to 25%. And then at 3 half-lives, we finally get to the 12.5% of carbon-14. Then we would multiply the half-life, which is 5,730 years, by the 3 years that we calculated, and we would get the answer 17190, or 17,190 years. 2. A rock is determined to be 1.426 billion years old. How much uranium-235 remains in the rock? So what we're going to do for this one, we're going to take our 1.426 billion years, divide it by 713 million years. That will tell us how many half-lives have occurred. With that, we will get the answer 2. And we know that at 2 half-lives, that'll go down from 100% to 50% in the first one. and 50% to 25% in the second. So we will have 25% of uranium-235 left. If X represents the half-life of potassium-40 and Y represents the half-life of carbon-14, write an expression that correctly compares the two half-lives. So X is greater than Y. So potassium-40 is 1.3 billion, which is greater than carbon-14's 5,730 years. All right, and that brings us to our lesson 1 check. So what method do geologists use to find the absolute ages of rocks? And they use radioactive dating. How could a geologist match the rock layers in one area to rock layers found in another area? And the geologist could look for index fossils in the rock layers and match them to fossils found in the other area. 3. A layer of sandstone sits above two other layers of rock. A fault cuts through the two lower layers of rock. How does the age of the fault compare with the ages of all three rock layers? So the fault is younger than both of the lower rock layers, but is older than the top layer of sandstone. A geologist observes rock layers that are folded. She determines that a layer of siltstone is younger than the layer of limestone above it. How can you explain the geologist's finding? So the limestone formed below the siltstone. After the rock layers formed, forces inside Earth raised and folded them, overturning their original order. 5. A scientist finds tools made of rock in the ruins of an ancient home. He also finds burned wood, likely cut by the tools in the home's fire pit. How could the scientist estimate when the tools were made? The scientist could use carbon-14 radioactive dating to find the age of the wood. The tools are probably about the same age. And that finishes lesson 1.